Hey, everybody. Let's talk about forces and how we use them. Forces have a magnitude and direction, as we know, and magnitude means a size or a length. It's telling us how much, and the direction is telling us where. That could be up, down, left, right, north, south, east, west, any sort of angle, somehow describing where that force is going. So let's talk about the types of forces. Okay, we have a variety of forces that we are interested in. The first one is weight, how heavy something is. We can call it the force of gravity, but we're not going to call it gravity all by itself. It is the force of gravity or the weight. If we wanted to know the weight of something, we could calculate that by using the weight equation, where weight equals mass times gravity. Weight is a force measured in newtons. Mass should be in kilograms, and gravity is in meters per second. And if you remember, gravity was 9.8 meters per second squared. Our next force is the simple push or pull force. It can go in any direction. We use an F with a subscript P to abbreviate the force of a push or a pull. We can also have a normal force, abbreviated F with a subscript N. A normal force is a support force caused by a surface. That's often a table or a floor or something like that. The normal force is always perpendicular to the surface. That means it's always at 90 degrees coming out of the surface. So if the surface is a table, that usually means the normal force points straight up. If the surface is a ramp, that means your normal force would be at an angle. Our next one is a tension. A tension is a force caused by a rope or a string or anything like that. A tension is always a pulling force. So if we have a rope or a string pulling on something, instead of describing that as a push or a pull, we would describe that as a tension. And lastly, the last force that we should know is the force of friction, F subscript F. Friction is a force caused by the rubbing of two surfaces, and friction is always pointed in the opposite direction. It's always trying to slow things down or prevent them from moving. And we're going to learn a little bit more about friction. Okay, there are two kinds of friction. The two kinds of friction are static friction. Static friction happens if the object is not in motion or the object is not moving or the object is at rest. Those are all the same thing. Static friction keeps things from moving. You'll notice sometimes when you try to push something, you have to push it a little extra to get it moving. That is you overcoming the static friction. The second kind is kinetic friction. We use kinetic friction if the objects are moving or sliding. So this is the kind that you're probably used to because you can see it when things slow down. If you roll a ball across the floor, the ball doesn't roll forever because kinetic friction is slowing it down. When we talk about friction, there's something that we use to describe the friction, and that's the coefficient of friction. The letter that we use is the Greek letter mu. So this is the Greek letter mu here. Mu, okay, it's a Greek letter, not an English letter. It is our coefficient of friction. So it tells us how much friction there is between two surfaces. The really cool part is every pair of surfaces has its own coefficient of friction. It'll tell us how much friction we can expect to find between those two surfaces. And one of the even cooler things is that static friction is always larger than kinetic friction. So it's always harder to get things moving than it is to keep them moving. Okay? Now let's see how we use these forces, and we're going to do something called a force diagram. So with the force diagram, we're going to take a situation and then we're going to describe the forces. So for our first force diagram, we're going to start with a box or a book at rest on a table. So here we have our box or a book, and it's resting on a table, and we should start with the forces that are acting on it that are pretty obvious. So we know that the book is going to have weight, so we're going to put a weight force on it. And the weight force always points down. And because our book is on a table, we know that there should be a support force, and we know that it's at rest, that it shouldn't be moving, so that this other force should be counteracting or going against the weight force, and that is going to be the normal force. So for a box or a book at rest on a table, we have normal force pointed up and weight pointed down. Let's save those forces. Those ones show up an awful lot. Let's look at a new situation. Let's do pushing of a box of frozen peas on ice. So there we are. We have special spiky shoes so that we can push across the ice, which is super slippery and therefore wouldn't have friction. So our box of peas has a weight, and if we have anything, it's probably going to have a weight force. And then we're going to have a normal force because it's on the ice, and that normal force will point up. And then because we're pushing it, we need to have a pushing force. So we can put a pushing force on it like that. But based on the way that we like to draw these, we don't want to put the pushing force here. We want the arrow to point away from our object. So we're going to move our pushing force off to this other side so that it points away from our object. So if we're pushing a box of frozen peas on ice, we have the weight down, the normal force up, and the pushing force pointed away from our object like this. Okay. Next one, we're going to take our box of frozen peas, and now we are going to be on carpet. So this time we're going to be very similar to the last one. There will be a weight. There's a normal force. And we're also going to be pushing it. But because we're on carpet, that means there's probably going to be friction. There's going to be some resistance to our push. And so there's going to be a friction force over here. So now we have 4 different forces acting on our one box of peas. And finally, we have a balloon. So if you're holding on to a balloon, there's all sorts of forces that are acting. So we need to specify which location we want to determine where the forces, what the forces are. So we're going to take this spot right here, the spot where our hand grabs onto the string that holds the balloon. Okay? So if we look at that one, instead of drawing the picture on it, we can draw the picture next to it, and we can represent that point of interest with a dot, and then we can draw on the forces that we have here. So there would be a pull down, that would be my hand pulling down on the string, and there would be a force up called the tension, which would be the balloon pulling up on my hand. This is the end of our video for forces and how we use them. Make sure you've taken notes. Of course, if you missed anything, remember you can pause, rewind, go back and forth however many times you need. If you have any questions, ask your teachers. Happy sciencing!